You can generate a lot of distribution. And we will review a couple of examples. First one is the logistic, for instance. Remember, we use PVD logistic with binary data or with growth curves. So f of x is 1 over 1 plus e minus x. This is the density of region. So we'll write that f of x equal u. Now we'll express x as a function of u. So that means 1 plus e minus x equal 1 over u, e minus x equal 1 over minus u over u. So the log is log of u over 1 minus u. So you pick a u from 0, 1, you compute this log u 1 minus u, and you have a logistic distribution. And I played with Weinbergs doing it. You can play with Weinbergs to use this distribution. When you write log of u of 1 minus u uniform, you don't need any data, just initiate a value, anything for u, 0, 2, and you get this nice histogram. And you can check, I have not checked, but you can check that the quantiles are very close to the theoretical ones. Another example is the Cauchy. How to generate a Cauchy? You will tell me that you don't use Cauchy. But if you have a true Bayesian, Bayesian are using Cauchy a lot now, instead of a norm for priors. And oddly enough, I don't know why, but there is no Cauchy in Weinbergs. And I remind you that the Cauchy is a ratio of two standard independent normal. This is also a standard T for 1 degree of freedom. But in Weinbergs, you are not allowed to put 1 degree of freedom in T. So you have no Cauchy. And I give you a simple recipe to generate a Cauchy. This is the density, and this is the CDF, 1/2 plus arc tangent x over pi. It was a nightmare for me, this slide, because I have to switch from old notation, French notation, to new French and to international, and at the end I was completely lost. So probably you have to make some correction. I don't know exactly. It seems that tangent is now TAN instead of TG. So anyway, you write f minus 1/2 equal arc tangent over pi. So you have to arc tangent. I think there was a mistake. Arc tangent equal pi and this. And now that means that x is the tangent of this quantity. Pi u minus 1/2. So you draw a u uniform, you compute this quantity, but u tangent pi u minus 1/2 is exactly put minus the tangent pi u. This is basic trigonometrics. And x and minus x has the same distribution. You can just compute the tangent pi u. And again, you can do that very easily in Weinbergs. Pi u, pi. I wasn't able to find the pi in Weinbergs. Does anyone know we can have directly a pi instead of introducing the value? Anyway, pi u. U is a uniform. I had some trouble with the bounds, so I could not take a 0 and 1. So I have to restrict a little bit the bound. And you write the cotangent, cosine over sine. And now it works. Here are the results for 100,000. And for instance, the quantile for 2.5 is 12.7, and for 10%, 3.08. The theoretical value and the observed value are here and here. So they are not very far from the theoretical ones. Another example is the Y rule, which is used in survival data analysis, that I will see as this density, cumulative density function. So you write u equal this. You have expressed x as a function of u. 1 minus u equal exponential minus x c minus xc log of 1 minus u. And x is minus the log of 1 minus u. 1 c. But 1 minus u has the same distribution as u, so you can just take u. Okay. So you compute this quantity, and this is a variable with parameter c. If c equal 1, you get the exponential. So very easy to do. Now this inversion principle can be applied also to the discrete case, not only to the continuous one, but to the discrete. Remember, in that case, the CDF is no longer a continuous smooth curve. It's made of broken straight lines. For instance, in that case, with 6 value, you start at 0, you jump from x1 to x2 with probability of x1, and you jump one step further from x2 to x3 with probability of x2, and so forth. So what you do here is very simple again. You pick a number in your 0,1 uniform generator. And you pick the x, the CDF is just above. Here is for the probability of x4. So you pick x4. So this can be applied easily, for instance, to the Bernoulli. You pick a uniform, Bernoulli with constant p. So if u is lower or equal to p, you have a growth on this Bernoulli. Extension to several categories. I don't know what is the extension. There is no name for the Bernoulli extension. Surprising. So it's a multinomial with 1, P1, P2, P3. I take the case of 3 categories. So if u is between 0 and P1, you retain xi1. If u is between P1 and P1 plus P2, you retain this, the response is the second category. And if it's P1 plus P2 between P1 and P2 and 1, you retain this category of response. So very simple to generate this extension of the Bernoulli. Now over transformation. The most famous one being the one used in the famous Box-Muller sampler of a normal. So what you do in that case, you sample U1 and U2 as IAE from U01, and you compute this strange quantity, minus square root of minus 2 log U1 plus sine 2 pi U2, and here the same with sine. And x1 and x2 are 2 independent standard normal growth. I was trying to know why this is this strange formula, so I tried to explain that. So the basic of the explanation is to make the polar transformation. Imagine you are in a plane, x1 and x2 are the coordinates of the point M. So if you make a polar transformation, you will write x1 equal r cosine theta and x2 equal r sine theta. But you want x1 and x2 to be normal. So x1 squared plus x2 squared are the sum of 2 independent normal squared. So this is mathematically r squared, but statistically is a chi-squared with 2 degrees of freedom. So in fact, you realize that your r will be the square of this chi-square. How to generate this chi-square? Very easy. You remember the link between a chi-square and a gamma. And we will use that a lot of time because in most software, they don't have directly the chi-square. So you have to get through the gamma. Chi-square with new degrees of freedom is equal to twice the gamma, standard gamma with nu over 2 degrees of freedom. And in that case, nu is 2, so this is 1. but we know how to generate easily a gamma with A being an integer. The sum minus the sum from 1 to A log of U, as many U as there are A. But A here will be 1, so we just take minus log of U. So my chi-square will be minus 2 log of a uniform. And I need R, so it's the square root of this. The length is the square root of this one. Now I want to enter in detail. Theta is an angle varying from 0 to 2 pi, so just draw it from uniform between 0 to pi, so 2 pi times the uniform 0, 1. So that gives you the previous formula. Now, it's not the most efficient one. And there are, you can avoid evaluation of sines and cosines. And this is now known as Marsagli algorithm or Atkinson and Peirce. So I just gave you here the recipe. You generate U1, U2 from U0, 1. You compute 2U minus 1. You take the sum of the square until it's lower than 1. If it's lower than 1, you compute this y, and you multiply y by d1 and y by d2, and x1 and x2 are two standard independent numbers. There are some modifications by Marsagli and Bray, and we recommend to use either this one or this one for the norm. No, the Box-Müller, not directly the Box-Müller, because it takes a lot of time to compute this cosine and sine. Other transformation useful, for instance, how to generate multivariate normal, mean zero, variance, covariance, sigma. This is very easy. What you do is you perform a Cholesky transformation of T of this covariance matrix. You know that. You can write sigma equal T prime, if T is a Lauer triangular matrix. So now, adding that, you generate X as P independent standard normal, and you multiply this vector of P elements, you can easily produce, by T. So, look, what is the variance of Y? Variance of Y is T, variance of X, T prime. The variance of X is by definition identity. So it's T prime, and T prime is sigma. Just what you wish. So it's very easy, the multivariate normal. Another one I like very much is based on convolution. You know, convolution has to do with the property of the sum of random variables. And everybody knows the famous central limit theorem, the strong law of large numbers, that if you add any random variable with the same independent and with the same distribution, you subtract its expectation, you divide by the square root of its variance, you will converge to, you will get the standard norm. So the problem is to choose this Z. We can choose anything. So we choose a uniform between 0 and 1. And we choose the sum from 1 to 12. Why? Because so 1 to 12, if you compute this quantity, 1 to 12 minus 6, but if you divide, what is the value of the denominator? 12 times the variance. But the variance of a uniform is 1 over 12. So 12 times 1 over 12, that means 1. Why? This will be a normal standard. It's not terribly efficient. It's not efficient at all, but this implement, if you want to generate, if you don't remember, if you are not a non-sum generator, you just do sum 12 uniform numbers, subtract 6, based on the central limit theorem. We can also use this convolution, sum of random variables, to generate the binomial or multinomial. Remember, the binomial is the sum of Bernoulli from 1 to the number of trials, B and P. Just in passing, in Wingbugs, oddly enough, I don't know, maybe some people from UK can explain to me, BNP is noted BPN. And so for us, the French people, it's really disturbing. Instead of NP, right here. So anyway, we know how to generate the Bernoulli, so we'll sum the Bernoulli from one direction. So the binomial, we will sum the Bernoulli. Probably for large n, you could find better generators, but you know for large n, you are tending to norm. So it doesn't make really difference. You can make also the expansion to the binomial. Remember, we have seen how to generate M1, P1, P2, so you will make the sum of this xi generated as the extension of the Bernoulli. Now we've finished with an example using the composition. I remember it's about the student. I remind you the definition of a standard student is a non-standard normal divided by independent square root of the chi-square divided by its degree of freedom. And this is in fact the square root of an f with 1 and new degrees of freedom. So remember the picture, as mu is increasing, you are tending to the norm. This is the Cauchy here, with thicker tape. The lower the degrees of freedom, the higher, the thicker the tape. So how you could do that using composition? In fact, you will represent your distribution as this stuff. If you have this density, you can write it as the conditional given x times the density of x, and takes for all value of x, taking the integral for all value of x. And now for the standard normal, we can easily find this g and h. What is g? G, the density of y given x, will be a normal with mean 0 and variance mu over x. And h for x will be a chi-square with new degrees of freedom. So what you do, you sample an x from your chi-square. We have seen before how to do it. And now having this xi, you put here in the variance, and you draw the y from this normal distribution. And you repeat that a number of times, and finally your yi's are a standard student realization. And you can extend that to find the picture. So I played again, just for fun, played with wind bags. Do it in wind bags. So remember, have to specify the normal 0. But here, something important again, in wind bags, you don't put the variance here. You have to put the inverse, the so-called procedure. So don't be confused. Anytime you use inverse, you have to put the inverse of the variance. So for the inverse of the variance, remember in my demonstration I had mu over x. This would be in that case x over the degrees of freedom, because this is the inverse of the variance. You will generate x from chi-square, that is a gamma alpha and half, but alpha being the degrees of freedom divided by 2. No data. So the data is the degrees of freedom, and the inputs are just if z equals 1, and so there is some mistake, should be x here, x equal 1. Change the notation, x equal 1. And now what you get is this. So this is for, that was for 5 degrees of freedom, your student distribution. And again, if you look at the quantile for this percentage, spherical value is 2.566, No, the theoretical is this one, and the observed is this one. So that is very close. So it works.
Could you show us? Because we didn't have this in the...
Yes, okay. It's just a game, you know. If you want to start easy thing in Windows, Windows obviously is not designed to do that. But it's fun to do it with Windows. So you will write the model, you open this parenthesis to close, you have the density of Z, define tau, you have to generate X, you have to define alpha, you have to data is the degree of freedom, and you give initial value Z equals 0, X equals 1.